Hello, my name is Christian Canham. I'm going to be going through the retrograde rocket landing simulation presentation that was presented at the 2021 International Modelica Conference. All right, let's get right into it here. So starting off with the background, so a little bit of background on how traditional rockets work. The rocket launches up in that upper atmosphere. What happens is the second stage of the rocket separates from the first stage. Second stage is what's carrying the payload, typically like a satellite or something, and it continues into orbit. The first stage traditionally basically just falls back to Earth, burning up the atmosphere or disintegrating in the ocean. If the rocket first stage is to be reused, though, a series of events occurs as depicted in this image on the right-hand side of the slide. So just going through a little bit of that. So these numbers correspond with the numbers on the picture. So the rocket first stage flips itself 180 degrees around. So the engines are now facing downward, downrange. Then what happens, number two, this boost back burn, and that's to slow down its horizontal velocity. Number three, this re-entry burn here, that's to slow down the rocket as it's re-entering the atmosphere to minimize excessive heating and damage to the engines. And then lastly, the fourth, we have a controlled landing burn where it's, in this image, it's landing on a little ship, a drone ship out in the ocean. And this whole diagram here, this is roughly mimicking the flight trajectory of the SpaceX Falcon 9 rocket, which is the best example of a real life rocket doing this. So there's a few key actuators on this rocket that really enable this first stage to be landed. One is these reaction control thrusters, these like compressed nitrogen gas thrusters that allow it to reorient itself. It does have grid fins that allow it to orient itself as it's coming down to the atmosphere. And then you also have extra oxidizer and fuel reserves to allow the engine to refire on reentry and slow it down. So all those items are not included on a rocket. That's the first stage is just disposable. So the simulation that I'm going to discuss in this slide begins right after one, starting at number two. So right as this boost back burn occurs. All right, moving on, let's go to model setup. So the landing procedure, as I mentioned, begins at second stage separation at altitude apogee, so the highest point in the flight trajectory for the first stage. And there is some key simplifications in this simulation to make the model creation a lot easier. So the first one is the flight path operates purely in a two-dimensional plane. So not dealing with the third dimension here, and that's somewhat justified by the fact that, the SpaceX flight example, the rocket launch, the stage separation of first and second stage, and the landing are all pretty much in a line in a two-dimensional plane. So if I'm mimicking that, then I can kind of make that assumption here. I'm also not modeling the curvature of the Earth's surface, and that is justified by the fact that the first stage is never actually in orbital velocity. It's a little under 50% orbital velocity, so I can make that justification. Moving on to initial conditions. So in the plot over here on the right side of the slide, we have actual real life SpaceX telemetry data publicly gathered from their podcasts. In the orange curve, you have the velocity, and green you have the blue you have the altitude. So what the goal of this model simulation is basically the landing. So as I mentioned, that's at apogee. So basically looking at everything in green. Everything in red here is takeoff. Everything in green is landing. So that's what I'm concentrating on. And then this border between the red and the green is my initial conditions. So we have the velocity, altitude is at the time 0 is directly taken from this plot. So we look at this orange plot and look over at this point, and we get about 293 meters per second. We assume because it's at the highest apogee that it's all in the horizontal direction. And then we also assume that, as I mentioned, this is after rocket reorients itself, so the engines are pointed downrange. And also mentioned up here, it's operating the two-dimensional plane, so we have the z-axis in the vertical direction and x in the horizontal. All right, let's move on to the model. So the model is split up into both the physical and the flight computer, all the algorithms. So in the physical model, we have the first stage modeled by this cylindrical multi-body part right here in blue. So that's representative of the Falcon 9 first stage. So it's 48 meters length, 3.7 meter diameter, and a 0.3 grams per centimeter cubed density. That density is pretty low because on the Falcon 9, most of that fuselage length is actually empty space on the inside with just the aluminum exterior. Moving on to the second bullet here, we have fuel consumption is based on total engine thrust, fuel and oxidizer burn in a 1:2 volumetric ratio. So that's modeled here in this fuel injector. So it's keeping track of how often the engines burn, and it's tracking up how much fuel is actually being used up here. Then we have the drag. So drag is modeled as a force normal to the rocket's trajectory, positioned as a force from the rocket's center of gravity. That's down here at the very bottom. And then for control of the first stage, we have these 3 grid fins and also the engines. So that's the physical model. Moving on to the flight computer. So that's split up into specific functions or algorithms that carry out a certain flight stage. So for example, landing, that would be one specific algorithm that would be modeled inside this flight computer. So we have various inputs to this flight computer. We have the clock, flight computer clock, velocity, position, and angle, which would all be categorized within a flight computer's IMU, or inertial measurement unit. And then we have certain outputs here, grid fin angles depicted on the right here, going at the top, going up to the grid fins, and then we have engine thrust and gimbal angles of the engine coming out the right side. So that's the top level model. Moving on to the actuator models, we have both the engines and the grid fins. So the engines, the flight computer controls the gimbal vector, which can be a plus or minus 10-degree angle with a 0-degree angle pointed normal to the end of the fuselage. And the flight computer also controls the thrust magnitude out of these engines. So these engines are modeled with a force vector at the base of the first stage, max of 2,700 kilonewtons. And that's again based on actual rocket engines on the SpaceX Falcon 9. Moving on to the grid fins here, we have 3 grid fins spaced evenly 120 degrees apart on the upper fuselage. And when those rotate, they impart a torque on the body or the fuselage of the first stage. Those allow it to orient itself and rotate. So the grid fin's effectiveness at rotating the first stage is based on the rocket's velocity. So higher velocity, more effective it is. Think about rockets in zero motion on the ground. Grid fins, they're not doing anything. Also influenced by altitude. Higher altitudes, you have lower pressure atmosphere, and so the grid fins essentially are working by redirecting airflow past the fuselage. If there's no airflow, not very effective. And then lastly, fin angle. So that's modeled in the sine wave here. So 45 degrees, most effective if you go beyond that, you're going to be past the point of effectiveness of the grid fin angle. And then we have, I mentioned 3 grid fins. 2 grid fins are parallel to the XZ plane, and those are simply preventing the rocket from rotating outside of this 2-dimensional plane. And then that 3rd grid fin is the primary one, the one that is being controlled by the flight computer. All right, so let's move on to the flight computer. So as I mentioned, we have different functions or algorithms within this flight computer, and those are depicted on the left-hand side here in these orangish yellow boxes. So starting from the top, we have the landing controller. This is a PD variant controller that takes in the rocket's velocity and altitude, and it controls the engine thrust and the grid fin angles to decrease those 2 velocities and altitudes, ideally to 0 at the exact moment the fuselage hits the ground. Then we have the boost back controller. So the job of that is to reduce the horizontal velocity for controlled reentry. And lastly, we have the entry burn controller, and that's a simple 30-second timed engine burn. Slows the rocket to minimize reentry heating. And these all control like the engines as well as the gimbal of the engines and the grid fin angles. So looking at our inputs, we have in green here, we have the IMU inputs. So that's position, altitude, velocity, and we have down here the angle of the first stage. And then lastly in purple, we have the outputs of our flight computer. So on the top here, we have the grid fin angles. So one angle for each of the 3 grid fins. And over on the far right, we have thrust vectoring that's outputted to the engines. So we'll go into a little more detail on what's happening in this grid fin controller, which is depicted in the top here. So the grid fin controller is split into a small and large scale signal controllers. So the small signal controller maintains the orientation of the first stage normal to the velocity vector. So without that, the rocket first stage would essentially just tumble out of control through the atmosphere. It keeps it pointed downrange, keeps it upright. And then we have the large signal controller, which orients the rocket from the horizontal to the vertical direction. So as mentioned, starting out, the rocket's pretty much laying flat, and it orients itself upright as it descends. And the large signal controller also guides the first stage towards the landing zone. So that's a predetermined destination on the ground where the rocket has to get to. So on the far right here, you see the model of the large signal controller. The top there, you can see this location controller. So that's looking at the position on the ground and adjusting the grid fin angle so the rocket can get there. That's just a PD variant controller. And then on the bottom here, we have this little ramp function, which orients the rocket from the horizontal lane based orientation, laying flat, to upright position. And on the bottom here, you can see a little plot of this ramp function in green here. And so that's target angle of the rocket. And we have the actual angle in blue here. So ideally the blue should be tracking the green perfectly. And then we have the grid fin angle here in red. So you see it pretty nearly tracks it. A little bit of under dampening here, a little bit of oscillations. All right, moving on to the landing simulation. So to simulate this, we tune the timing of the controlled engine burns until the first stage was successfully able to land. So for example, in this previous flight computer model, we would basically tune the parameters of the timing of when these controllers would activate in order to get a nicely controlled landing. And the landing was considered successful if the first stage rocket landed within a 50-meter diameter of the landing zone point. Number 2, if the landing was successful if it's less than 2 meters per second velocity, vertical velocity at the ground. So obviously, if the rocket's coming in hot, if it's faster than 2 meters per second, that would be considered a crash in real life. It would not be considered successful. Lastly, third, fuel reserves are not depleted. So as I mentioned before, the fuel and the oxidizer, those volumes are tracked. And if those reach 0 before the rocket touches the ground, it's considered a failure. All right, so we have the flight controller is basically robust against varied initial conditions, as seen in the plot on the right here. So you can see 4 different initial conditions, varying initial velocities. So we have some slow ones, we have some fast ones. See, the successful landings are shown in green here, and the unsuccessful one is in red. So in this case, the initial velocity was too slow. The landing controller, the grid fins weren't didn't have enough control authority to bring the rocket first stage all the way over to the landing pad. That's a failure. But these other examples, success, and it shows that this model is a little bit robust against varying initial conditions here. So then we'll compare the simulation results to actual SpaceX telemetry data. So the SpaceX data is shown in red here, and this Modelica model simulation is shown in blue. So you can see pretty nearly tracks it all the way down to the landing burn, a little bit of offset there. You can see it overlaid the different engine burns in the different flight phases over top. So you have the boost back burn, the upright maneuver, the entry burn. You can see it slowing down the rocket here, and the landing burn. And on the y-axis here, we have the altitude of the rocket. On the x-axis, we have time. And lastly, we'll go over the visualization and conclusion. So visualization. So sometimes it's difficult to understand the flight maneuvers from just these 2D plots. Difficult to appreciate it and difficult to share with those who may not be familiar with your work. So that's where this visualization library comes into play. And that makes it very easy to basically attach this library's predefined visualization bodies to existing physical bodies on your model. And it allows you to basically play an animation and see the actual rocket. So in this example, this is a little screenshot of the simulation. We have the ground modeled, Cape Canaveral below here, and we have the first stage modeled in the grid fin. So if this were to play, as it did when we first created it, we have this engine thrust down here. So this will expand and contract based on what the engines are doing. Some more thrust will elongate, and then this grid fin angle will rotate corresponding to what the flight controller tells it to do. So it's good visualization and telling what the rocket's actually doing, and you could actually place cameras around it to actually track this in real time. You can even potentially put on like a VR headset and track this as it's coming all the way down from orbit, landing at Cape Canaveral here. And lastly, conclusion. So this simulation demonstrates basic control fundamentals in recovering a rocket's first stage by landing a rocket vertically back on Earth. It's a good approximation for SpaceX Falcon 9 first stage landing maneuver. Despite all these key simplifications, it is proof of concept that you could take relatively simple building blocks and add to them over time to create a pretty meaningful simulation that's visually compelling. And that is all I have. Thank you, everyone, for listening, and take care.